Welcome back to this lecture on algorithms. In the third segment, we will discuss the binary search algorithm, which is a solution to this problem. This problem is slightly different from the one we've talked about before because there's an extra requirement on the objects in the sequence and the target object. You must not only be able to tell if two objects are equal, but if they are not, you must be able to compare them and determine which one is less than the other. And furthermore, the object in the input sequence must be sorted from smallest to largest, or in ascending order. So that's the problem that binary search is supposed to solve. So let's look at this algorithm. Don't forget to specify the inputs and outputs of the algorithm and the general behavior of the algorithm in an initial comment. This comment is identical as the one before with the extra constraint here on the input sequence. The first line of the algorithm must start with the keyword function, since this algorithm returns a value, the name of the algorithm, and then in parentheses the comma-separated list of inputs with their associated type. So make sure to specify in this case that the input must be in ascending order in terms of the sequence. Now the function must have a return value and its type must be specified. In this case, it's an integer. Now we're ready to start the specification of the algorithm in our pseudocode. This algorithm will use two variables. L, which stands for left, is the index of the first or leftmost element in the input sequence, and R, for right, is the index of the rightmost or largest element in the sequence. The algorithm will work iteratively, so we're going to have a while loop, and the way this algorithm works is going to look for the target in the middle of the sequence. So suppose you're trying to find a particular page in a book. The fastest way to find a given page is to open the book approximately in the middle, compare the target page with the page that you just opened it at, and if the target is larger than the page you're just looking at, you can eliminate the first half of the book, and then you can focus your search on the second half of the book. So now you're looking at the second half of the book. In this case, L and R would be updated to indicate that range of the sequence of the book that you would look at. So L would be the index of the middle page or the page you were looking at. R would still be the end of the book. And then you would iteratively look at the middle of that range of pages and look for the target there and keep going until you found the target. So we're going to have a while loop, specify the termination condition later. But the first step in the loop, remember, is to open the book at the middle of the book. In other words, we need to find the middle index between L and R. And this is done by adding up L and R, dividing by 2. And since we need an integer, the index into the sequence is an integer, we just take the floor function of that. M stands for middle. It's the index in the middle of the range of values that we're looking at. Then we compare the target with the element at that location in the middle of the sequence. If the target is greater than A sub m, meaning we can ignore the first half of the sequence, then we move the left pointer to the element right after the middle, in other words, m plus 1, and we don't change the right pointer. In the other case, when the target is not greater than A sub m, then we want to consider the first half of the sequence. So we want to ignore the second half. In other words, we want to move the right pointer to the middle of the sequence, and therefore we're considering the subsequence from L, which hasn't changed, to R. That's the left half of the sequence. So we're going to keep doing this, and notice either L is going to increase or R is going to decrease. And so what's going to happen is at some point L and R are going to meet, and so we're going to stop the loop when that has happened, mainly when it's not the case that the left pointer is to the left of the right pointer. When this is false, meaning L and R have crossed paths, then we can stop the binary search. Now the algorithm is designed in such a way that when we exit the while loop, the target object is at index L if it is in a sequence at all. So all we have left to do is to compare the target object with the element at position L. If they are equal, then we found the target object and we can return its index, namely L. Otherwise, the algorithm guarantees that the object, the target, is not in a sequence, and we can return -1. Now, we'll let you think about the correctness of this binary search algorithm. I'm going to go through just one example trace of it on the following input. Let the sequence be the following letters. Notice they are sorted in ascending order, alphabetically speaking, as required by the algorithm, and let the target be the letter D. So we're trying to find the position of D in this sequence. Notice that n is equal to 9, and the indices of the elements go from 0 to 8. Now, let's start the trace of the algorithm. L and R are initialized to 0 and 8 respectively, which is the first and the last element in the sequence. And now we start executing the first iteration of the while loop. Is L strictly less than R? In other words, is there still a non-empty range of elements to consider? And the answer is yes, 0 is less than 8. So we start the first iteration of the loop. The first step is to compute the position of the middle element. 0 plus 8 divided by 2 is 4. So m is equal to 4. Notice I indicate the values of the variables L, M, and R by their position right under their value. Now, we can compare the target element D with the element at position M, A sub 4. D is not greater than H. Therefore, we are going to move the pointer R to M. In other words, we're going to assign to R the value 4. And that is the conclusion of the first iteration of the loop. So now we're back at the top of the loop and we're about to start iteration number 2. Notice that the value of L has not changed, so we compare L and R. Is 0 strictly less than 4? The answer is yes, so we start the second iteration. The first step is to compute the new value of M. 0 plus 4 divided by 2 is 2. Now, we can compare the target D with the value A sub 2, which is D. So is D greater than D? The answer is no. So we're down to the else case, which means we are going to assign to R the value of M, which is 2. And that concludes the second iteration of the loop. Now we're back at the top, considering starting the third iteration, but first we have to compare the value of L, which hasn't changed, to the value of R. 0 is indeed less than 2, so we start the third iteration. We again compute a new value for M. 0 plus 2 divided by 2 is 1. And now we compare the target D with the element A sub 1, which is B. In this case, D is greater than B, so we execute the then case. And L gets updated to the value M plus 1, that is 2. And that concludes the third iteration of the while loop. Back at the top of the loop, considering the fourth iteration, notice the value of R has not changed, so now we compare L and R. Is it true that 2 is strictly less than 2? The answer is no, and we exit the while loop. So notice that throughout the algorithm, L has been moving from left to right, R has been moving from right to left. We reach the point when R and L have met. So at the end of the while loop, all we have to do is check whether the target D is equal to the element at index L. The answer is yes in this case. Therefore, we have found the position of the target object. Its index is L equal 2, which we return. And that is the end of this trace of the algorithm. Now, I strongly encourage you to study this algorithm carefully, especially if you had never seen it before, and trace it in other cases. For example, choose a different target here for the same sequence. Choose a target that is not in the sequence and make sure the algorithm returns the correct answer. And that is the end of this segment.